So let's work out this example together, and then at the end I will switch to Mathematica and show you how to visualize these, and we'll talk briefly about one way to interpret what we're actually doing. So let's dive in. So we're going to compute the surface integral of this vector field f, and I'm going to give you a surface parameterized by this particular parameterization. Nice bounds here. These are going to be nice. They're just constant, so that's good. So we know what to do. If we go back up to our formula, right, this is the formula that we need right here. And so let's just copy that actually so we don't have to rewrite it. And we'll plop it down here. So we can say, okay, look, this particular integral that we want, the surface integral of f dot ds, bold S there, vector S, is the same thing as this particular double integral, and that's going to be the key. So what's nice about this is if you have the formula in front of you, it's like a recipe, and it tells you the ingredients that you need. You need this, and you need this. So, sorry, f of r of u and v. So let's begin by computing r partial u, and what do we get? We get 1, 1, and then a v, and r partial v, we get what? 1 minus 1 and then a u. And so I'll let you check this. You can compute this yourself, but if you take the cross product, you should get u plus v, v minus u, and negative 2 is what I got. Okay, I don't have to compute its length, by the way, because in the end, right, the length cancels out. I just need this r partial u cross r partial v. So that's nice. And the formula, the setup for these surface integrals of vector fields, right, there is a unit normal vector, but when you actually go to compute it, the dividing by the length actually cancels out, and you just end up with this. So we've got the first part. Now f of r of u and v is pretty easy to write down. Let's go ahead and do it separately just to make it clear. So f of r of u and v, well, I can't see my f anymore. F is what z, x, y, so I just plug in whatever the z component of r of u and v is, uv, and then I plug in the x component in the y component of f, I plug in the x component of r of u and v. That's kind of confusing. U plus v, and then I put, let's see, u minus v in the z component. So that's what we end up with, and I don't know if I can squeeze this in or not. Let's try. So the point is the integral that we want of f dot ds, this becomes the double integral, and the bounds for this double integral are over whatever the restrictions are on u and v. Well, that's clear. They're just 0 to 1, 0 to 2. So let's go ahead and set the bounds up. We're going to go du dv. We got to not forget that order, du dv. And then we're going to have f of r of u and v, so uv, u plus v, u minus v, and then we're going to dot with ru cross rv, so dot with u plus v, v minus u, and minus 2, and then we said dA usually, but we said dA is going to be du dv. And so, wow, you just set up your first surface integral of a vector field. Congratulations. Give yourself a high five. I'm going to need to add more space. Let me zoom out. Ooh, boy. Yeah, we can just drag this down. Put a little note there to myself not to forget to do Mathematica, which we won't. All right, so I don't want to spend too much time on the computational details, but just enough to make sure that there's no confusion. So we're just going to take the dot product, so this times the, let me clear my highlighter, this times this, plus this times this, plus this times this, and I'll let you compute it, but when you do that, you should get a u squared v plus u v squared plus v squared minus u squared minus 2u plus 2v du dv, and you can work it out. It's just a polynomial, kind of tedious, but it's not that bad, and so you'll end up with 6. All right, so let's switch to Mathematica, and then we'll come back and we'll ask ourselves, what does this actually mean? All right, I wanted to show you a visual of what you're actually doing. So the blue arrows represent the vector field f that we just worked over. right? Our formula for F was what, ZXY. And so that gives you some sort of visual. And then I went ahead and graphed the surface that we're working with, and we limited what U and V could be. So we get a limited surface here. The surface does not actually extend in all directions. That's the only piece of the surface that we care about. And so what, that's a nice visualization. You can see the surface in the middle of the arrows, but what does the surface integral actually mean? And so one way to think about it is that the vector field is representing fluid flow, let's say, and I'm going to think about my surface as this thin net, this infinitely thin net that doesn't actually stop anything, but it's just there, and the water, the fluid is flowing through it, and the surface integral, the flux, is just measuring how much of the flow goes through the net. And you need a positive sense and a negative sense. And so when you pick an orientation, that's flow going through the net in that direction is going to be positive, and then the opposite direction is going to be negative. And so you can specify the orientation of your surface, which way is sort of in and which way is out, which way is up, which way is down. You do that when you orient it, when you pick your normal vector. And so that's what flux can represent, was one way to think about it. And even though maybe over an electrical, when you're working with electrical engineering, modeling different electrical magnetical fields, even though that's not a fluid, this way of thinking about it, my understanding is still helpful, and it's still perhaps the right way to think about it. So, when you're working with surface integrals of vector fields, I just imagine my surface being this nice little net, and I'm just measuring how much of the fluid is flowing through the net. And that's one way that you can interpret these. So I hope that's helpful. We'll break this video here, and then we'll go to the next one. I've written down a few of those comments in the notes, and so I'll point that out in the next video.